Good afternoon. How to esteem derivatives of different orders. Take your copybooks, take your pens, and begin to write down. Let a function y is f of x be differentiable on some segment from A to B. Generally speaking, the values of derivative f prime of x depend of x, which is to say that the derivative f prime of x is also a function of x. Differentiating this function, we obtain the so-called second derivative of the function f of x. The derivative of a first derivative is called a derivative of the second order or the second derivative of the original function and is denoted by the symbol y to prime O f to prime of x. Y to prime is y prime prime on f to prime of x. For example, if y is x to the power of 5, y prime is 5x to the power of 4, y2 prime is derivative of 5x to the power of 4, or 5 times 4x to the power of 3, 20x to the power of 3. The derivative of the second derivative is called a derivative of the third order, or the third derivative, and is denoted by y to 3 prime or f 3 prime of x. Generally, a derivative of the nth order of a function f of x is called the derivative of the derivative of the n minus ones order and is denoted by the symbol Y with upper symbol N inter bracket or F nth of x. The order of the derivative is taken in parentheses so as to avoid confusion with the exponent of a power. Derivative of the fourth, fifth, and higher order are also denoted by Roman numerals. For example, the derivative of the fourth order the fifth order, etc. Here, the order of the derivative may be written without bracket. For instance, if y is x to the power of 5, then y prime is 5x to the power of 4, y2 prime is 20x to the power of 3, y3 prime is 60x to the power of 2, y4 prime, fourth derivative, or this symbol, is 120x, y fifth derivative is 120 and then derivative all then derivative last derivative sixth derivative 7 etc. equals 0. Consider example. Example 1. Given a function y is e to the power of kx. K is constant. Find the expression of its derivative of any order n. Solution. The first derivative is k times e to the power of kx. The second derivative is k squared times e to the power of kx, etc. The nth derivative is k to the power of n times e to the power of kn. Other example, let's y is sine of x and we must find nth derivative of the function y. Solution. Y prime. The derivative of sine is cosine of x, or we can write down sine of x plus pi over 2. Y2 prime is minus sine of x, or sine of x plus 2 times pi over 2. Y3 prime is minus cosine of x, or sine x plus 3 times pi over 2. Y4 prime is sine of x, or sine of x plus 4 times pi over 2, etc. And we can think that y, the nth derivative of the function y, is sine of x plus n times pi over 2. In similar fashion, we can also derive the formulas for the derivatives of any order of certain other elementary functions. The reader, the student himself, can find the formulas for derivatives of the nth order of the function y is k to the power x to the power of k. Y is cosine of x. Y is natural logarithm of x, for example. The rules given in last theorems for the first derivative are readily generalized to the case of derivatives of any order. In this case, we have obvious formulas. Y u plus v, n prime is the nth derivative of u plus the nth derivative of v, and constant times u, if we calculate, the nth derivative of cu, where c is constant, we have c times the nth derivative of u. Let us derive a formula called the Leibniz rule of formula that will enable us to calculate the nth derivative of the product of two functions u of x times v of x. To obtain this formula, let us first find several derivatives and then establish the general rule for finding the derivative of any order. Let y is u times v. Y prime will be u prime v plus u v prime. Y2 prime is u2 prime v plus u prime v prime plus u prime v2 prime plus u prime v plus u prime v prime plus u v2 prime, or u2 prime v plus 2 u prime v prime plus u v2 prime. Y3 prime equals u3 prime v plus u2 prime v prime plus 2 u2 prime v prime plus 2 u prime v2 prime plus u prime v2 prime plus u v3 prime, or u3 prime v plus 3 u2 prime v prime plus 3 u prime v2 prime plus u v3 prime. Then the fourth derivative. Same way, we have u fourth derivative of u times v plus 4 u 3 prime times v plus 6 u 2 prime v 2 prime plus 4 u prime v 3 prime plus u times the first derivative of v. The rule for forming derivatives holds for the derivative of any order and obviously consists in the following. The first, write down the rule for forming derivatives. Hold for the derivative of any order and obviously consists in the following. The first, the expression u plus v to the power of n is expanded by the binomial theorem. It means u plus v to the power of n is sum from 0 to n c k from n times u to the power of k v to the power of, sorry, not boundaries, k v to the power of n minus k on c n 0 u 0 v n plus c n 1 u 1 v n minus 1 plus c n 2 u 2 v n minus 2 plus etc. plus c n u n v0. And in the expansion obtained, the exponents of the pole of u and v are replaced by indices that are the order of the derivatives, and the zero power in the n terms of the expansion and replaced by the function themselves. It is step 2. Write down it. nth derivative of the function y equals u times v in prime equals nth derivative of u times v plus n times n minus 1's derivative of u times v prime plus n times n minus 1 over 2 factorial times n minus second derivative of u times v to prime plus etc. to u times nth derivative of v. This is the Leibniz rule. A rigorous proof of this formula may be performed by the method of complete mathematical induction. In other words, to prove that if this formula holds for the nth order, it will hold for the order n plus first. Consider example 3. Let y is e to the power of alpha x times x squared. Find the derivative of nth order. Solution. U is e to the power of alpha x. V is x squared. U prime is alpha times e to the power of alpha x. U2 prime is alpha squared times e to the power of alpha x. U3 prime, etc. to nth prime is alpha to the power of n times e to the power of alpha x. V prime is 2x. V2 prime is 2, and all other derivatives of the function v is 0. Or nth derivative of the function y is e to the power of alpha x times alpha to the power of n times x squared plus 2n alpha to the power of n minus 1 times x plus n times n minus 1 alpha to the power of n minus 2. Our next theme, differentials of various orders. Suppose we have a function y is f of x, where x is the independent variable. The differential of this function dy is f prime of x times dx, is some function of x, but only the first factor f prime of x can depend on x. The second factor dx is an increment of the independent variable x and is independent of the value of this variable. Since dy is a function of x, we have the right to speak of the differential of this function. The differential of the differential of a function is called the second differential or the second order differential. Of this function and is denoted by d second of y. It is differential of the function y. Let us find the expression for the second differential. By virtue of the general definition of a differential, we have d second y equals f prime of x times dx prime times dx. Since dx is independent of x, dx is taking outside the sign of the derivative upon differentials, and we get d second y equals f2 prime of x times dx double. When writing the degree of a differential, it is common to drop the bracket. In place of dx squared, this, we write dx squared. Same. To mean the square of the expression dx, in place of dx cubed, we write dx cubed, etc. The third differential of the third order differential of a function is the differential of its second differential. This 3y is d of d second y is f2 prime x dx squared prime dx or f3 prime of x dx cubed. Generally, the nth differential is the first differential of a differential of the n minus 1th order. The nth differential of y is differential of n minus first order of y, or f n minus first derivative of x times dx n minus first prime dx, or nth derivative of x times dx to the power of n. Formula first. Using differential of different orders, the derivative of any order may be represented as a ratio of differentials of the appropriate order. For example, f prime of x is dy over dx, f2 prime of x is d second y over dx double, etc. The nth derivative of f of x is the nth differential of the function y over dx to the power of n. The second formulas. It should, however, be noted the equalities 1 and 2 for n is greater than 1 hold only for the case when x is an independent variable. Our next topic: different order derivatives of implicit functions and of functions represented parametrically. The first. An example will illustrate the finding of derivatives of different orders of implicit function. Let an implicit function y of x be denoted by the equality x squared over a squared plus y squared over b squared minus 1 equals 0. Differentiate with respect to x all terms of the equation and remember that y is a function of x. We have 2x over a squared plus 2y over b squared times dy over dx equals 0. From this we get dy over dx is minus b squared x over a squared y. The first equation we denote by number 1 and this number 2. Again, differentiate this equality with respect to x, having in view that y is a function of x, we have the second derivative of the function y of x is minus b squared over a squared times y minus x times dy over dx over y squared. Substituting in place of the derivative dy over dx its expression from the formula 2, we get d second y over dx double equals minus b squared over a squared times y plus x times b squared over a squared times x over y squared. Or, after simplifying, we have d second y over dx double equals minus b squared times a squared y squared plus b squared x squared over a to the power of 4 y cubed. From equation 1, this equation, it follows that a squared times y squared plus b squared times x squared is a squared times b squared. Therefore, the second derivative may be represented as the second derivative equals minus b to the power of 4 over a squared y to the power of 3. Differentiating the latter equation with respect to x, we find d over dx 3 times, etc. The second, let us now consider the problem of finding the derivatives of higher order of a function represented parametrically. Let the function y of x represented by parametric equation x is phi of t, y is psi of t, where t depends from t0 to capital T. 3. The function x is phi of t has an inverse function t is t of x. on the interval from t0 to t. dy over dx equals dy over dt over dx over dt, the fourth formula. To find the second derivative of y of x, differentiate 4 with respect to x, bearing in mind that t is a function of x. It means d over dx of dy over dt over dx over dt or d over dt of dy over dt over dx over dt times dt over dx. 5. But differential with respect dt of dy over dt over dx over dt equals dx over dt times d with respect dt of dy over dt minus dy over dt times differential with respect to t of dx over dt over dx over dt squared. Or sorry, here c or dx over dt times d double y over dt double minus dy over dt times d double x over dt double over dx over dt squared. Dt over dx is 1 over dx over dt. Substituting the latter expression into 5, we get the second derivative of y with respect to x equals dx over dt times the second derivative of y with respect to t minus dy over dt times the second derivative of x with respect to t over dx over dt double. This formula may be written in more compact form as follows. The second derivative of y with respect to x equals phi prime of t psi 2 prime of t minus psi prime of t phi 2 prime of t over phi prime of t cubed. In similar fashion, we can find the derivatives d third y over dx to the power of 3, the fourth derivative y, and so forth. Consider the example. A function y of x is represented parametrically. X is a cosine of t, y is b times sine of t. Find the derivative dy over dx and the second derivative. Solution. Dx over dt equals minus a sine of t. The second derivative of x with respect to t is minus a times cosine of t. The first derivative of y with respect to t is b times cosine of t. The second derivative of y with respect to t is minus b times sine of t. It means dy over dx is b times cosine of t over minus a times sine of t, or minus b over a times cotangent of t, and the second derivative of y with respect to x is minus a sine of t times minus b sine of t minus b times cosine of t times minus a cosine of t over minus a times sine of t cubed, or minus b over a squared times 1 over sine cubed of t.